This is the second part of the carboxylic acid derivative chapter. We're going to be talking about amides. So let's get started. And the first thing we're going to do is that we're going to actually just learn how to name the amides. But for that, I'm going to have to introduce to you the acetyl group. I know you know it, but it never hurts to actually just review it. So this is the acetyl group. Notice that it's the main component of acetic acid. If I had acetic acid, I would have the OH over there. But we are in the amide chapter, and instead of a carboxylic acid, we can have an amide. So I'm going to attach a nitrogen to my acetyl group, and I am going to call this acetamide. Notice that there's a little bit of a pronunciation issue here, amides, but when you're saying it, you say amide. Just make sure that you pronounce it right. Now, I have my acetamide right here, but there's a methyl attached to the nitrogen, and I have to specify that that methyl is on the nitrogen and nowhere else. To do that, we are actually going to use a capital N to specify that we're talking about the nitrogen, and then we're going to put the substituent that's on the nitrogen. So there is a methyl attached to my nitrogen, and the rest of my compound is my acetamide. If you happen to have two different groups, make sure that you tell me twice what you have and where they're attached to, and you put them in alphabetical order. So I have a methyl and I have a propyl group. Methyl goes first. So I have a methyl attached to the nitrogen. And then attached to the nitrogen, I also happen to have a propyl group. I ran out of space. Make sure that you keep it in one line because I'm going to put the acetamide at the bottom. So we're going to end it in amide so that we know that we have an amide. Now this one's a little bit different because the carbon of the carbonyl is not part of a long chain. I have a cyclohexyl attached to it, and this happens to be an amide. This group right here, it's a carboxylic acid, but it's an amide. It's one of the derivatives, so it's a carboxamide. And I have the cyclohexyl on it, so I'm going to put cyclohexyl. Remember that we use the YL to specify that it's a substituent attached to something else. It's not part of the main chain of carbons. And my parent is the carboxamide I have. Alright, I have two cyclic amides right here. And two cyclic amides are, well, the cyclic amides are actually commonly known as lactams. Same way that cyclic esters are called lactones. But, interestingly enough, we are going to name the lactam as if we were naming the cyclic ketone. So I have cyclopentanone here, and cyclopentanone has been changed a little because in the second position now I happen to have a nitrogen. And to specify that it's a nitrogen, I'm going to use azo. So azo means that I have a nitrogen atom, and it's on the second position of my cyclopentanone. We're going to do exactly the same thing here, but this one would be a cyclohexanone, very good. You still have the nitrogen on the second position, and as long as you have a lactam, the nitrogen will be on the second position. So this is a 2-azo cyclohexanone. So this is a systematic name for lactams. This is the way that we're going to go and name them, if we name them. Again, when you go to the back of the chapter, you're going to have problems, and it's easier for the publishers to actually put the name. It occupies less space than a picture. But let's go to the common naming of these ones, because when you're naming with a common name, they use the Greek letters. So alpha, beta, gamma. This one would have the alpha, the beta, the gamma, and it goes a little bit further to the delta. But we specify that the nitrogen is attached to the gamma carbon. And we're going to use the word lactam, so we don't have to say that it's an amide. But 1, 2, 3, 4. This is 4 carbons. It would be a butyroic acid. So lactam, sorry. Needless to say, we're not going to go with the common naming of lactams. This one is a valorolactam, so it goes even further, or deeper perhaps I should say, into the common naming. But I want to point out that we know of a very famous beta-lactam. So let's do the backbone of a beta-lactam. If my carbonyl is right here, this would be the alpha carbon, this would be the beta carbon. The nitrogen would be attached to the beta carbon. So this would be the basic backbone of a beta-lactam. And the most famous beta-lactam that we have would be penicillin. Of course, penicillin has a sulfur and esters on this side and more groups attached to the nitrogen. But the basic backbone of the lactam is the beta-lactam. Oh dear. Okay. We don't have as many reactions of amides as we had of acyl chlorides or esters, but we can reduce an amide to the amine. And of course, we're going to use lithium aluminum hydride for that one. But it's important that you remember that we are going to reduce a carbonyl all the way down to a CH2 with lithium aluminum hydride, so we get the amine. Why do I say this? Because all the other derivatives of carboxylic acids will be reduced to primary alcohols. Amides are reduced to amines, and that's a big difference that you know the professor is going to put in the exam. Alright, so remember lithium aluminum hydride, 2 steps. The second step is what I call the quenching. People call it a workup, but I have 4 hydrides right there. And I'm going to simplify the mechanism quite a bit. You know how I like that one. So the hydride attacks the carbonyl, and the aluminum and the oxygen, aluminum loves oxygen, so they get together. The oxygen now has a negative charge, so it forms a bond to the aluminum. And just for a little bit, we're going to form a double bond between the carbon and the nitrogen. When I form that carbon-nitrogen double bond, I'm going to kick out the oxygen. So that's important because we have never seen the oxygen leave this. In this reaction, it leaves. We form an imine. We have seen imines before. And what's going to happen to it? Well, I still have 3 hydrides attached to my lithium aluminum hydride. So another hydride comes, and now I'm going to break this bond, give the electrons to the nitrogen, and here's your amine. Technically, it's a very simple mechanism. This is the new step, looking at the oxygen being the leaving group. So lithium aluminum hydride adds 2 hydrides to it because it has plenty of hydrides. What happens if we use dibol? How many hydrides are in dibol? Dibol, if you remember the structure of dibol, diisobutyl aluminum hydride has only 1 hydride. Just 1. That's it. So we're going to actually have to do the mechanism for this one because it's going to give us a little bit of a difference. Again, sometimes I simplify too much, but the hydride, the dibol attacks the carbonyl, and it gives you a tetrahedral intermediate. Here's your hydride, here's your nitrogen, still there. The aluminum is going to go and bind to the oxygen, That's what it likes to do. It has two isopropyls attached to it. We are going to go ahead and reform. It's almost the exact same mechanism as the previous one, except that I don't have enough hydrides. Alright, so we reform the carbonyl, we kick out the leaving group, and now something is gonna happen. Hold on, I'm trying to build interest in this. Alright, this one right here, carbon-nitrogen double bond, this is an imine. This is a salt of an imine because my nitrogen is positive. But the important reaction right here is that whenever you hydrolyze an imine, so you add your water and you add a little bit of acid, notice, those are workup conditions, we are going to get the carbonyl back. And when we get the carbonyl back, it's an aldehyde. So even though the lithium aluminum hydride, LiAlH4, gave us the amine, when we use dival, we only have one hydride. So when we hydrolyze the imine, the intermediate imine, we get the aldehyde. So far, dival has actually produced aldehydes out of all the derivatives of carboxylic acids. So we have a little tiny problem right here. We take this. Now, this is an amine, and on this side, what do we have on this side? Do you recognize that? That's an acetal, and that is a protected carbonyl. So this carbon, the carbon that has the two oxygens coming off of it, that is a carbonyl. And somehow they do the reaction with lithium aluminum hydride. They work it up with a little bit of dilute acid, and they get a cyclic imine. So we need to find out what's happening right here. So let's go ahead. Well, this is a protected carbonyl, so the lithium aluminum hydride is not going to see it. So obviously we're going to be reducing this amide on this side. So just with lithium aluminum hydride, LaH, I will not remove the protecting group. It will still be there. But I will reduce the amide to the amine. By the way, this is a primary amine. Now the problem starts right here in that quenching. That's where things go wrong. So when you add water and acid, you think you're going to be cleaning up your aluminum salts and your lithium salts, but you're also deprotecting the carbonyl. So for a little bit here, we are going to get the carbonyl. And now we have to go to the aldehyde and ketone chapter, in which we have a ketone reacting with a nitrogen that has two hydrogens. We are going to eliminate water out of this reaction. And in the process, we're forming a 5-member ring. So this is going to be a nice favored reaction. And the nitrogen will replace the oxygen. We will not change the position of the double bond. So this is still an imine. And that's what's happening right here. When we deprotect under the dilute acid workup, we actually just get the ketone that will react with the amine, the primary amine that's on the right side. Now we go with nitriles.